Welcome to the Material Minds podcast, the place where we talk to the people exploring new materials for a better world. I'm your host, Srikrishnan Shankaran, and our guest today is Markus Koch, the head of the Physical Analytics Core Facility here at INM. We had a really exciting conversation, a lot of fun, about how you can use advanced physical analytical methods like electron microscopy and X-ray spectroscopy to study really unusual samples like ancient paintings, pizza, blue water, and silver nanoparticles and so on. So it's really, it's an episode filled with fun stories and interesting anecdotes. I enjoyed it a whole lot. I hope you do too. And so here we go. Welcome, Markus, to Material Minds.
Thanks for the invitation.
Yeah, absolutely. And so, you're a very interesting person to get to know. And I'm sure our listeners and our viewers are going to get to know you throughout this podcast, throughout this episode. We're going to do it through the game that you're aware of, 3 truths and a lie. You have 4 statements prepared. 3 of them are true. 1 is a lie. You're going to tell me each of them. I'm going to kind of dig into them a little bit. And I'll try to figure out which one is the lie. So if you're ready, just go ahead with the first statement.
Okay, so my first statement is, several weeks ago, we had Leonardo da Vinci here in this house, or at least part of a quite famous painting.
Okay.
So that's my
first
statement.
You had the Leonardo da Vinci painting. Is this for business or pleasure?
No, it's for business, for sure.
Okay.
Maybe it's too expensive to have this just for pleasure, but it's due to science, scientific questions.
Okay, can I ask you what you had to look into it scientifically?
Yes, so usually these paintings, science behind, so how they are painted, how, for example, also the degradation of these paintings over the centuries happens is of great interest. Mm-hmm. And at this time was Da Vinci from Munich. Mm-hmm. It's there in the so-called Alte Pinakothek. And the lady from the Leibniz-Institut came to me to do backscattered electron imaging of the whole cross-section that they will first investigate in Grenoble at the CERN with X-ray, synchrotron,
and
micro-diffraction.
What do they want to know about it? Like, is it how degraded it is?
Exactly. So usually they used lead white as the whitish part, typically the background, and depending on the kind of painting, this lead white corrodes to different phases. And as far as this lead is quite good visible with backscattered electrons and electron microscopy, we can have a nice overview of all these different corroded parts. Well, then at CERN, they can nicely take a closer look with X-ray diffraction on a microscale. To distinguish these different phases of this corroded lead white.
Okay.
So
instead, but are you studying that with your method, or are you using a different method to understand something else about it?
So that's tricky because depending on the scientific question, you have to look closer. For example, for the distinct phase. So if, for example, this corrodes to lead acetate or some other things, you need to know the crystallographic phase that I cannot determine by backscattered electron imaging. But I can see where these phases are concentrated. That these guys then can have this closer look exactly at the position that I found. Because with a light microscope, you will not see this in such detail compared to an electron microscope. Oh, wow. So it's a support of very special analysis that guys in Grenoble do, actually now in July.
Okay, wow. Okay, this could be fact or fiction, knowing what goes on at INM. Maybe one last question is, how did you come to be the person who was contacted to look at this painting?
Yeah, so as far as quite long here in the Institute, there's a long history about so-called archaeometry. So we started with an old window from a castle here in Saarland,
Okay.
where a lady asked me, you got the SEM to do analysis without coating, so I can directly take a look on the small piece of a window. And then, step by step, other guys get to know me and brought other stuff. And so it's a long story. And as far as this instrument is very useful for this kind of materials, it's quite, wouldn't say heavily booked, but quite often used for such analysis.
Oh, okay.
Yeah.
So you've built up your rep in archaeometry to get to the point of a Leonardo da Vinci painting.
Yes,
now.
so there was a conference last year in Austria regarding also a panel, so-called Schloss Tirol, a quite famous panel from the 14th century, and we presented, me and a student from Munich, and she lives in Saarland, so it's the connection, that she can come here to share investigations. And then we gave a presentation together, and the guys were convinced that this, how we do it, is quite fruitful for this kind of analysis.
Okay, and the word archaeometry itself, is it like measurements in archaeology? Is that
paintings, also old stones, so you can have a lot of things that you find somewhere.
Okay. Something from the past.
Exactly. That maybe covers this topic.
Okay. Okay. Interesting. Yeah. So that's a tough one. Now you start off with a tough one. Okay. Let's go for your second statement, and then
my second statement. Yeah. So as far as our SEM also has a heating device, so we can heat up samples. We also investigated pizza.
Okay.
So both from biotechnological point of view and also together with the company.
Yeah.
And so the experiment is you create a small pizza, and then with yeast, so everything you also use at home.
Okay.
Yeah. And then you put it on your sample holder, this heating device. And then you can take a look while heating what happens on this pizza. So how gases come out, how it's burnt, up to 250 degrees. And this you can visualize by electron microscopy.
And this is with all the parts of the pizza. It's not just the dough or just the tomato.
you can decide what do you like to see, with salami, with mushrooms. You only need to have the small.
How small?
8 millimeter in diameter.
Oh, your first statement was pretty wild, but I don't know if this is even wilder.
Yeah, but that's a dimension of our heating
paper.
I
mean, it makes sense, but I'm wondering who's making that kind of a pizza.
It's in vacuum, so it's vacuum based.
Okay.
But you can nicely compare these results with the actual pizza that you see at home. So if you look in your oven, you can see how this changes, and the results are comparable to this.
Okay.
Yeah.
Was this for a certain pizza company?
So it's without telling names, a quite famous one in Saarland.
Okay.
And so they had interest to visualize this. So
Do they have the best pizza now? I mean, maybe after off the record, you can tell me, and I'll order from them from now.
Yeah, maybe. But so I buy it quite regularly.
Okay.
Yeah.
Okay. Okay. So how do you get the heating conditions, because pizzas, you put them in certain type of ovens, like there's a stone oven pizza or whatever, the regular type of oven pizza and so on. They're the frozen pizzas and things like that. And apparently, depending upon the oven, you get a different quality.
Exactly.
Are you able to mimic this kind of oven quality in your electron microscope?
Partly. So we have this heating device is ceramic based. It's quite fast. So now depending on the heat that you can transfer, it's more or less fast. And depending on the thickness that I create on this 8 millimeter diameter sample, it's different. So we cannot compare to all kind of ovens. And we remember correctly, we didn't correlated with how long, for example, this frozen pizza was waiting until we heat it up.
Yeah.
But generally, you can find out, for example, how fast, for example, it needs, or the time necessary that cheese melts. Something like that.
And you're able to see cheese melting with the electron microscope?
Yes, sure.
Okay. Because my understanding is you can't see too deep into the material, right?
But the cheese is usually on top.
Yeah.
And this I can nicely
This you
visualize.
can see, okay. So then in that perspective itself, how thick can you have your pizza if you want to see different layers?
With 8 millimeter diameter, so for sure I do not make 2 centimeter pizza. So it's a relatively thin one. So I prepared under the stereo microscope, this pizza with some tomato and cheese, and depending which type, mushroom, small piece. And then I can follow these parts that I prepared on stereo microscope also correlatively in the SEM.
Okay.
Yeah, that I know where I put which piece, and then I heat it up and take a look at given temperatures, what happens with mushroom, with cheese at the given place. And so that's the idea.
So the way you're saying it, did you make these pizzas or did you get like little samples made from whoever?
Firstly, I made the pizza by my own.
Okay.
And lately, say somehow did some reference pizzas, that I investigated with the heating table in the SEM.
Okay. Man, if this is a lie, you're a really good liar. Like this, because you had so many details within it. This is tough for me to figure out. Okay, let's go to the third statement. Let's try to see.
Let's try.
Yeah.
So the third statement is regarding bluish drinking water. Okay. So there was a case in Heidelberg in March 2019 that they found that the drinking water in Heidelberg is bluish. Okay. Slightly bluish. And they thought, maybe it's something regarding copper cobalt complexes that make it bluish. And they did everything and didn't find out that there's a chemical impurity there. And then they asked several institutes if they can look for some microcrystals that can scatter the light to make this water slightly bluish. And they gave me one example, the so-called Blautopf. There's a small lake in Baden-Württemberg. And so I took a look, and so they asked me if I can search for calcite microcrystals in this water.
Okay.
And so they sent me samples, and I took a look at the sample that he wants to cheat me. It's not bluish, And then I asked this guy, and he told me, it's bluish, I can show you images of bigger volume, where you can see it more nicely, that it's bluish. And then I used with our SEM, cryo, we can also do cryo SEM, and also cryo TM to find these small microcrystals of calcite. And I was successful. So I found this, and then in the newspaper you can read that this is caused by calcite microcrystals. This bluish color, and that's not dangerous. It's just an agglomeration agglomeration of smaller crystals that lead to a scattering that usually is not there in drinking water, because that's usually transparent and not slightly bluish.
Okay, and calcite is calcium.
Calcium
just
carbonate.
A certain crystalline form
of
calcium carbonate. Okay.
Exactly.
Okay, and it's a certain crystalline form of calcium carbonate that's agglomerated in a certain way that it scatters the light. Exactly. That blue is sort of what reaches your eye.
Exactly.
Okay.
Yeah.
Okay. And you detected this with the cryo-electron microscope. And the cryo-electron microscope, you still need to bring it down into vacuum and froze, or into a frozen state, basically?
Firstly, to freeze it and to keep it frozen. And then in vacuum, depending on the temperature, so less than minus 90 degrees, it will not sublimate this ice. So I have a stable condition. Also to do EDX and imaging. And by EDX, I can check the composition.
Sorry, EDX
is a chemical analytics based on X-ray. Based on X-rays, of the energy of X-rays. So when you put electrons on any material, we usually cause X-rays to excite, and this you can collect. And if you have a spectrometer that can detect this by energy, then you can detect the elemental composition.
Okay.
And then I found calcium,
Okay.
a little bit carbon, yes, that's hard to detect. And oxygen, yeah, you have to assume because all the water is oxygen if you freeze it.
Yeah.
So by that, we were quite sure that together with the background of the scattering, also with the Blautop story, we were sure it has to be calcite.
Okay. Okay. Yeah. So, what was the amount of calcite in this water that it was actually able to make it blue?
It's not different to usual drinking water.
Okay.
Yeah. So if you disperse it finer, or if it's dissolved, if it's not agglomerated to calcium or calcium carbonate crystal or form that it's colloidally dispersed in the system, it's just there. So if you look at drinking water, chemical analysis, also on mineral water, you see that's calcium inside, more or less. But it's still transparent.
Yeah, okay.
It's a form of the agglomeration that makes this slightly bluish color.
Okay. And so the water in Heidelberg was also the same calcite and also from this lake that you talked about?
No, it was different. So this lake is far away from Heidelberg.
Yeah.
And usually where this drinking water was got from this kind of a hill where it's collected in underground, it was never bluish before. And they think that it's due to a dry summer, that this water somehow differently dispersed this calcite to get this crystals that scatter the light.
Okay.
So there's something going on that we do not know underground where they take the water out.
Yeah.
But the result was slightly bluish.
Okay.
And
but
it's
harmless.
It's harmless. In the end, it's harmless because we could also exclude everything else.
Yeah.
So no copper, no cobalt that usually gets some bluish color in water. And also none of organic contaminants.
Okay. Yeah. Okay. That's interesting. So you also know it's no dye of any sort.
Exactly. No other dye than this crazy calcite crystals. Yeah.
Okay. Okay, that's also, I mean, everything you've said so far is just very convincing, like in the way you said it. And I cannot detect a lie yet, or I can't detect which is the lie yet. So let's go on to your fourth statement.
My fourth statement. So with drinking water, we can also do a nanoparticle preparation. So what I prepared here for you is drinking water. From Saarbrücken, so it's transparent, it's not bluish. So usually what you can get in the bathroom. And then I put 2 silver wires inside.
So it's a glass vial with drinking water and 2 silver wires inside.
Exactly,
okay,
2 silver wires. And then what we can do, so we can take this nice 9 volts and we can create 27 volts if we plug them together. Then we have more power to do preparation of silver. No, it does not fit together. Maybe we have to do it differently. No, this does not work. Then we take 18 volts. We have to take it this here. Okay. And and then I will explain why this starts and hopefully everything works because I...
Okay, just for our listeners, you have 2 9-volt batteries connected in series.
Yes.
And now you're getting electrodes from the terminals to the silver wires that are within the glass vial with just drinking water.
Just drinking water.
Okay.
Yeah, so slightly conductive. And now I start the experiment.
Connected.
And
we wait. And it's bubbling.
It's bubbling and we will see it's more going on. And the story behind, so this, what I do here with this easy experiment is a PhD work of a quite famous Swedish scientist.
Okay.
And so he did his PhD in 1907, so it's quite long ago. And interestingly, he created 30 different metals in this colloidal or nano form.
Okay.
And he received a Nobel Prize, 1926 in chemistry, for something completely differently.
Okay.
So and this Swedish guy called Theodor or Theus Svedberg. So he received his Nobel Prize for the creating the ultracentrifuge.
Okay.
I'm sure you know this.
Yeah.
And he started with something typical from electrochemistry like that. and he ended in separating proteins.
Yeah.
By the ultracentrifuge.
Okay, so ultracentrifugation is just like a machine that spins stuff really fast.
Exactly, really fast.
Yeah, really fast.
So this was a development
yeah.
in these times,
But okay, are these two connected in any way, or was he just doing two different things? And
so it's maybe old-fashioned. It's for sure connected because as you can see, so something's going on.
Yeah.
So, and with this easy setup, I cannot say the particles all are 5 nanometers or 10 nanometers or 15 nanometers.
Okay.
So they are somehow size distributed.
So these are silver nanoparticles coming off the electrodes into the water.
Exactly.
Just because of the voltage you've applied across them.
That's an easy story. So
yeah,
that's a lot of science behind and how you can change the setup, different current, different additives, and what you will see, it becomes more and more dark brownish. So while creating these silver nanoparticles, they also grow, they agglomerate. And the question or the challenge is then, can we somehow separate them by size?
Okay.
And now think about a guy who has a lot of nanoparticles of different sizes, how we can separate it.
Okay. Well, how did he know that it was nanoparticles back then?
Yeah, so at these times they used a light microscope in dark field, so-called Siedentopf microscope.
Okay.
So it's a scattering effect that you put light from the side to your sample, and then you can see the color of your sample, and the color due to the plasmon resonance, tells you how big are your particles.
Oh, okay.
So they knew this without an electron microscope.
Yeah, that's incredible.
This was developed in the 30s.
In the 30s?
In the 30s of this century.
Wait, he did this in 1907?
Exactly.
And he waited till the 30s to figure out...
No.
Not he waited, but he
waited, but with light microscope, he even could decide how big are the particles.
Oh, he could?
He could,
in
by
the
color.
range.
In the nano range.
By the color, okay.
He saw in the light microscope. So he couldn't see the particle size.
Okay.
He could only see the color of these particles.
Yeah.
And guys that made theory could tell him, if they are bluish, then they're 10 nanometers.
Okay.
Yeah.
Okay, so now that I'm looking at it, it's gotten quite brown and murky. There's still probably some gas being generated from one of the electrodes. There's from the other electrodes, it looks like something's kind of peeling off slowly, and it gets more and more murky as we speak.
Yes. So more and more particles are generated by this easy setup.
Easy setup, okay. All right, so 4 statements, even a demonstration in one. All 4 were convincingly delivered, I have to say. The fact that you brought a demonstration makes me think there's no way this can be a lie. But on the other hand, maybe you kind of use that tactic to sneak in a lie there. Okay, let's just recap the 4 statements so that I know what's going on. First one is Leonardo da Vinci.
Yep.
Painting here at INM, and you use some of these advanced techniques, X-ray techniques, to figure out how much damage has happened.
So we use electron microscopy to support the guys with the X-rays in Grenoble.
Yeah.
They do this.
So that's the first one. The second one's pizza. To study how heat affects the different components of the pizza. And you had 8 millimeter sized tiny pizzas, which just blows my mind. Okay, and then the third one, what was
drinking water?
Drinking water. The bluish drinking water with calcite in it.
Yes.
Which you were able to detect. This was in Heidelberg. It was a real thing that happened, and you got water from a lake and you detected it. And the fourth one is the generation of silver nanoparticles, and
and the connection to this
ultracentrifuge.
Thijs Svedberg and ultracentrifuge, yes.
Okay. And you've demonstrated that to me right now. Okay, I've got to make a choice now. I think I'm going to go with the pizza.
Your pizza, don't believe me.
I don't believe your pizza.
Okay.
I mean, just because I find that to be the wildest thing.
Wildest.
Yeah.
That's really the wildest one.
It is the wildest one?
Yeah. So also we did pizza, but not to 250 degrees and also not with the company.
Okay.
We did it once to demonstrate yeast, how it works.
Okay.
and only to 50 degrees.
Okay.
So then I stopped.
Okay. So it's actually partially true.
Yes,
in
he could
principle.
do
Yeah,
this.
it could, yeah. Okay.
He
Okay.
could do this, but
Okay.
there was no company in Saarland motivated to do this so
okay.
far. Maybe they will be. I don't know.
So it's not just a lie; it's a project proposal, basically.
Yeah, but internal, yeah. So
Yeah, sure,
nothing
yeah.
that I would say, that has to be done now. Or
Well, if there's any pizza
tomorrow.
companies out there, then
maybe
they're
they
probably
see
excited.
Exactly.
Yeah. So okay, the Da Vinci was real then.
Da Vinci was really.
Okay, I was kind of unsure between the two of them. The water one with calcite. I haven't heard about it, and I wouldn't have known one way or the other. Actually, if this would provide the blue color, basically. And whether you would have actually detected that over here. So I wasn't sure about that, but it sounded plausible to me. And this one, there are so many historical details here. There could have been a lie snuck in there, but still the pizza kind of jumped out to me a little bit.
Yeah, so you found out the right one.
Oh, well,
Yeah,
okay,
congrats.
that was a tough one. And I even asked you so many questions about that. Yeah,
sure, but I was prepared.
You were well prepared. Yes, absolutely. Okay, maybe we actually already discussed all of the statements quite a bit, but I'd like to dig into some of them a little bit more. So the Da Vinci one, what I wanted to ask actually, and I forgot to ask at the point, was if you detect certain types of damage, is this going to inform people how to repair it, or just how to store it, or what?
So this is really, really a long story. So depending on the corrosion, it's maybe partly possible to somehow refresh it to the original state. But usually the corrosion is going on so long and so heavily that there's no way to restore it completely.
Okay.
So then the guys from restoration, they have to find ways, and they have a lot of experience, how to somehow restore it in a way that it looks perfect.
Yeah.
And with information, for example, provided by SEM or light microscopy or infrared spectroscopy or Raman, so know different ways how to do it better or not.
Yeah, okay.
And that's something. So I was really convinced. I was in Innsbruck for this conference when someone showed me so-called reconstruction of something, a wooden part of an altarpiece, that he did 1 year, reconstruction of original one. He copied this to find out how they could made this, 700 years ago.
Wow.
To see all these features, how it's possible to adapt, for example, gold leaf on the surface, how they do their painting on top of the gold leaf and so on, So and it's really nice to see that these guys use reconstructions, so they make this, adapted to historical ways, and then see the result, and then check out possible. Oh no, that's not possible. It looks completely different.
Yeah.
That's the way I was really convinced.
Okay.
To do this more often also in science. So
absolutely.
if this is true, so repeat it. This way how it looks like. And if it looks differently, especially if you have an SEM that can look much closer, then you are convinced. No, that's not the way how they did this.
Yeah. Okay.
Yeah.
Nice. Okay, so you're reconstructing, or you're figuring out the methods.
Yes.
You're basically doing forensics.
Yes.
About how they probably did it back then and try to reconstruct it today.
Exactly.
And you're able to characterize what's been done today and compare it with what was done back then.
Especially if you reconstruct it with modern, for example, gold leaf. This student is, figuring out how gold leaves are used and thickness and also mixtures of silver and gold, so-called Swiss gold. And by looking at these old altar pieces, paintings, you see something, you think, how is possible that thin layers of gold leaf? How did they did this? How have they done this? How have they put gold leaves together? And then you try to reconstruct this and find out, no, it's not possible just to put it together. It's less distance between this leaves and so on. And it's really fascinating what you can visualize then by an SEM with this.
Wow, yeah, that's absolutely true. Okay.
So, in the end, I did nanotechnology also in the mid-age. because
without knowing.
Or even with knowing, for example, that scattering of light through one leaf, lets them still transparent.
Yeah.
So if you look through the gold leaf, you can so looking against the sunlight, you see a color, and then they knew that's the right thickness.
Ah, okay.
Yeah.
But these are around like 20 or 50 nanometers or so,
Yeah,
right?
so roughly 100 nanometer, a little bit less,
That's
a little
really
bit more.
tiny. Okay.
Yeah,
Wow.
and to save money then in the later mid-age, they put very thin gold onto silver leaf.
Okay.
To let it look like gold,
Okay.
but to cover it mechanically better.
Yeah.
Yeah, so they use 30 or even less thick gold on silver. But unfortunately, silver corrodes quite heavily by all these years. And then in the end, you only see a very thin gold layer. And silver chloride, silver sulfide in these ancient samples.
Wow, and this is what you figured out by these kind of forensic methods with electron microscopy and X-ray diffraction.
So by nice preparation from the student and then with an SEM together, then we can do a lot of nice investigations with these old paintings and altar pieces and
wonderful.
So on.
Are you allowed to say what painting it was or which one of Leonardo da Vinci?
Yeah, this was the Madonna of the Carnation.
Okay.
So this you can see in Munich.
Okay.
And they brought two pieces to check for the investigation in Grenoble. And so usually if you already put some small pieces, so there's maybe 200 micrometer in size because you don't like to scratch a bigger part. And if you once have scratched a small part, you should do as much investigation as possible. And as far as we do not do too much with this, so this iron polishing maybe changes some 100 nanometers only. And if you think about it, it's 50 micrometers thick, so we are not as destroyable as other techniques.
Okay.
And that's why they also like to ask us, because we can can receive a lot of information without destroying these seldom pieces. Because nowadays you are not allowed to take any pieces.
True.
Of these important,
Absolutely. And are you insured in a certain way while doing these measurements? What if you're trying to put it in your machine and you kind of tear it or something?
So these are small pieces and they're embedded in resin, so usually don't get and that's how they are stored usually. And they can be 100 years old that guys put it out for other investigation, and then you can collect them. It's allowed, so they have to write a proposal. So we want to do another analysis with now better instruments in Grenoble, and before we go to Grenoble, we want to check it in Saarbrücken, and then they come and you're allowed to take a look at this quite seldom piece of Leonardo da Vinci.
And so which museum is it in
This
Munich?
is so-called Alte Pinakothek.
Alte Pinakothek. So I can't say that.
Alte Pinakothek. I'm not sure if there's an English translation. And it's under the supervision of the Dörner Institute. So that's the institute that take care of all these paintings that are there and many things more.
And it's visible to the public.
You can go there. You can see this.
Nice. That's what I'm going to do next time in Munich.
When you're in Munich.
I'm very curious. When was this done? Was this, you said a couple of months ago or something?
I guess 2 months ago.
2 months ago, okay. And it's back there now. Oh, no, you just got a tiny piece.
A tiny piece, and this is should be now in Grenoble.
It's now in Grenoble, okay.
Exactly.
The whole painting.
No,
only the piece.
Sorry, yes.
I keep,
that's the reason why we image everything on the small piece, that they know where to look for.
Okay.
So the painting, usually you can investigate also by X-rays, but then without touching. So then you have a big instrument, and then you check, for example, regarding iron, lead, and X-rays, and you can see how they painted this.
Okay.
That's a really huge investigation, and that's done
incredible.
on site, not at Saarbrücken.
Okay. I can imagine. Well, this water has now turned close to black even.
So we can maybe
quite
stop
dark
it.
Brown.
We have dark brownish silver nanoparticles, so the usual color is not as nice as for gold. So for gold we have this nice reddish color with the agglomerated bluish. But with this, from medical point of view, they're quite interesting. So we also
They're
did some
antimicrobial.
exactly. That's
Yeah.
your stuff. You know it. And we can do some coatings with these particles inside. Also use the silver nanoparticles, for example, for conductive layers. Yeah, to put it in polymers. So that's what, for example, Tobias Kraus is actually doing.
Absolutely. Yeah.
And we had a long tradition with silver nanoparticles in this house.
And so is that then your favorite material? That
It's one of my favorite materials because I shared it with a lot of guys here in this house from preparation point of view. Even now, so also with analytical regular, for example, we did also publication with this to measure the activity of silver ions in different biological media. And it's really nice in this house if you can share this from chemical, physical, and biological point of view. I guess it's something that makes this house unique.
Yeah. INM is known for nanoparticles, and
now
you get a lot out. Can you say approximately what size these particles might be?
So between 5 and 30 nanometers.
5 and 30. So is that based on the voltage that you applied that you get this, or what?
More or less time. So at the beginning, when it's less brownish, they are smaller. As long as you do it without stabilizing agents, they grow. So what you can easily do, take a droplet on a TM grid and then check out by TM.
Transmission electron microscopy.
Exactly, transmission electron microscopy.
Okay.
And then for sure you can optimize this. So this is from 1907. I've already said, but there are several guys up to now still optimizing this procedure. Because it's quite easy. You get a lot of particles from just a silver wire. And you can use for sure also higher voltages, AC voltage, different stabilizing agents, and so on. So it's quite flexible, the synthesis.
Okay, so it's super easy to make, and there's a lot of stuff you can do with it, and there is a lot of stuff being done with it already as we speak, as we say, and that's actually very interesting. And all these things that you talked about now brings us actually to our last section pretty much, which is that it seems like you've had a lot of freedom. If you've also almost gotten to getting a pizza into the SEM, then you've had a lot of freedom and fun, I would say, at INM. In the last segment, basically, I want to bring up that our Federal Ministry for Research and Education, the BMBF, has declared this year's topic of science to be freedom. And well, I want to bring this up. I don't have the best segue, but actually talking about freedom, recently you were also in this Stadtradeln competition or event, basically. So it's a city cycling event where you basically just cycle every day for about 3 weeks. And it doesn't matter how far you cycle, but you can just record it in an app. You were part of the INM team, so the team in INM, which was part of the bigger team of the University of Saarland, and you were the top cyclist with 1,500 kilometers in 3 weeks, 21 days. 1,500. I did 150. Which I'm very proud of. How does one get to 1,500?
I did it not the first time. So I knew this with our kids in school. So I also supported this. So I knew how it works. And for sure, if you are a little bit sportive or somehow also ambitious in something called athletics, so track and field athletics, you can nicely combine this. So sitting on the bicycle for me means a lot of freedom. You have a nice landscape, so there are nice rivers like Blies, Saar, and my favorite Klan, where you can go by bicycle and you just enjoy. And you only need this time on a race bike, and then you collect these kilometers. So that's a story. It's not only it's a city bike where I do my shopping. It's also nice, that I can do this because I live next to the city. But for sure, I collect a lot of kilometers on my race bike.
Okay.
And starting with the competition in Hamburg. So there was a competition, and this is 30 kilometers. And as far as I only took 2 shoes for this competition, And I had time, so
Yeah.
I took this bike, and then you collect 60 kilometers at the first day. And
Okay,
if you
yeah.
go to the bakery and something, though it said it was 90 kilometers the first day.
Yeah.
By accident, yeah. And then, yeah, so that's it, yeah.
Yeah.
And then you continue, and the weather was quite nice. So the last week was a little bit rainy.
Yeah.
But on the last Saturday, I decided, regardless if it's raining or not, go again to the Klan River.
Okay.
And I managed, and then I was able to reach this distance.
That is absolutely incredible. And I can remember, especially on the first day, I was filling in I was very happy. It was a Sunday. I thought okay, I'm gonna go my max. I did 20 kilometers. I was super happy. Of course, I have a city cycle.
Yeah.
Not really
Not
a sports
race bike,
but still, I was very happy about my achievement. And then I saw 90.
Oh, I'm sorry.
Oh my gosh, no!
I'm sorry, Shirish.
I was very happy. You're part of our team. We now topped the university teams. Not that it was a competition. It's about environmental health and so on.
The first and other thing
health.
is you find out what is possible using a bike. Yeah, also shopping, also going for competition, for example. Yeah, you do not have to carry much. Yeah.
Yeah.
And it's really nice to use a bicycle. It
absolutely is, and I mean, you are someone who appreciates freedom in that sense so much, and that's also seen in your work. So maybe we just end with maybe your thoughts on freedom in science in general. What do you feel about it?
Yeah, it's a long story. Or maybe one story of our last director, Professor Arzt. So he remembers days at Max Planck where there was the so-called Friday afternoon experiment. So something you can decide to do, if you're interested in anything, and that's very important, especially, for example, if you run an SAM, with a lot of options, for example, this pizza, I can do it, but you have to do it somehow, to get the experience. If this is possible, what you can see, what is not possible, and by that, by this idea, to take time that is unplanned for any kind of experiment. This is something, I would say, this is freedom.
Yeah.
And that is absolutely necessary in science. That's my personal point of view.
That's beautiful. Freedom is a Friday afternoon experiment in science. And I completely agree with that. That's wonderful.
Nice.
It was really fun talking with you, Marcus. I think we'll need a whole other episode again to cover some more stories. I know your life is filled with a lot of stories.
Lies.
Yeah, this was still an excellent lie, and it was partially the truth. And I'm curious if any pizza companies are going to call you up.
Okay, let's
on this.
see if they call me. Yeah, thanks so much, Shirish.
Wonderful, Thank you everyone for listening and for viewing. So we had Marcus Koch, we had a bunch of wild stories, the time flew, and I had a lot of fun. So we're on social media sites, we're on YouTube, we're on your favorite podcast sites. You can catch us in all these places, subscribe, all of that stuff, and watch out for the next episode. See you.
See you, bye-bye.